So for today's pre-lecture video, I wanted to take some time to look at damped and forced harmonic oscillators. This comes at the end of the chapter. It's interesting information, and I didn't know if we would get to it in class. I also want to stress that really these two topics will be looking at it in a more qualitative way, more than mathematical, simply because we don't really have the techniques available to us to solve these, the differential equations that result when we have damped or forced harmonic oscillators. I mean, they are actually easily solved if you have a knowledge of differential equations, but we don't really have that at this stage. So basically, when you put a mass on a spring and you let it oscillate, while we say that it will oscillate forever in a perfect world, we probably realize that in the real world, those oscillations are going to eventually dissipate or die out. And this is because the oscillations are actually damped. What we want to do is we want to sort of have a better understanding of what's going on when we have the damped oscillation. And just to be clear, what we mean by damped oscillation is that the amplitude of the motion gradually decreases over time until basically the oscillation will come to a stop. So when we had a normal oscillator, we only really just looked at the force of the spring, which was equal to minus kx, was equal to the mass times the acceleration. And so the equation that we ended up solving that allows us to look at the harmonic oscillator was this differential equation. So when we're talking about damping, there's going to be a damping force. And this damping force we're going to say is equal to minus b, which is just a damping constant times the velocity. So in this situation, we're making the conscious choice, which is usually pretty accurate, that the damping force is proportional to the velocity. An example of this would be the drag that you might experience in air, or if you put the oscillator in a fluid. So if we look at that then through F equals ma, then our force, we have the force due to the spring, the force due to the spring plus the damping force is equal to the mass times the acceleration. This actually changes the differential equation because keep in mind velocity is also the derivative of position with respect to time, and we can somewhat rearrange this, and our differential equation that we would be solving would be look like this. And so just for kicks, this is a second order differential equation because the highest power of derivative is the second derivative. It's also called homogeneous because all the values that involve x, which is our solution, all that which is on the left-hand side is equal to 0. So the solution to this equation, the x as a function of t, is what we're talking about that would describe the motion. Like I said, we don't know how to solve this differential equation yet, but that's okay because you'll learn eventually. But the solution, here's the solution right here. And so we still have the oscillating portion of the motion that we had before, but then notice this amplitude is different. This amplitude is an exponential decay, and because as t goes on, this is just going to get smaller. And so this amplitude acts sort of like an envelope for the oscillation to take place within. We'll look at a picture in a minute. And so the oscillation really will continue. It does happen at a different omega. It's not the omega we saw for the regular oscillator, so it's omega prime. And you can see here the damping constant is in the amplitude, and that's how it affects it. So if you think about it in a really qualitative way, this solution makes sense. This is the new value for the oscillation, omega prime. Notice that it's related to the restoring force of the spring, but it's also related to the damping. And this is what the oscillations will look like. Notice that they still are going up and down like a cosine wave would, but the dotted line represents the amplitude that we saw out in front. And that is what I said. It's like an envelope. And notice that the peaks go up to that location, to that envelope, which is, of course, decreasing in amplitude over time. This is really a picture of the damped oscillation. So what omega ends up looking like is going to depend on how these two factors are related to each other, because it ends up that we have basically three types of damped oscillations, and all three of those are determined by the relative strength of the damping force compared to the restoring force. So let's go through those. The first is called critical damping. In critical damping, we don't have any oscillations. If this oscillator is released from some initial amplitude, it actually will come back to equilibrium without going through an oscillation. Critical damping means that it comes to that equilibrium as quickly as possible. And so the condition for critical damping is that omega is equal to 0, which means that k over m is equal to b squared over 4m squared. And so we're going to define these in terms of the damping constant. So here, b is equal to 2 the square root of k times m. So if the damping constant is related to the restoring force in this way, then we're going to have critical damping. Overdamping is basically when, again, there are no oscillations, but basically the damping force is much stronger than the restoring force. And so what happens here is the b squared over 4m squared is greater than k over m. And you see that what happens then is that b will be greater than 2 square root of km. So now b is greater than that critical value. But you also might notice that if b squared is greater than 4m squared, omega is going to be equal to the square root of a negative number. Omega prime is imaginary. But like I said, this is a situation where you're not going to have oscillations. And we'll look at it in a moment, but the difference between critical damping and overdamping is like something that will come back to equilibrium without oscillating, but it'll do so more slowly because the damping is so strong. It kind of brings it back to that equilibrium very slowly. Finally, underdamping, we do have oscillations, and this is probably what we really think of when we think of damped oscillations. Here, k over m is greater than b squared over 4m squared. So b is actually less than that critical value, and we would have oscillation. So let's take a look at all three cases. Here, notice this is a picture of the different types of damped oscillations. Notice this one is the critical damping, and see how quickly it comes back to equilibrium compared to the overdamped, which you see comes much more slowly. And then the other solid lines represent different stages of underdamping. that allow for some oscillations to take place, but the amplitude is decreasing over time. And now we want to just take a really quick look at the idea of forced oscillations and resonance. Basically, the difference here is when I have an oscillator, but instead of just letting it kind of go through its motion on its own after giving it an initial displacement, what if we have a driver, something that is applying a force in a very regular way? It turns out that when we have that situation, what's going to happen is there will be a particular frequency that the driver will, for the driver, so that if you have a driver at that frequency, you actually will get the largest oscillation amplitude. And so we call that situation resonance. An example that I like to give of this is pushing a child on a swing. We all learn very quickly that there's a certain rhythm to how I want to push a child on a swing to get the child to go to ever increasing amplitudes of motion. If I push the child very randomly, I could actually end up getting almost no amplitude of motion. And so I think this is a good example of resonance and force oscillations. So when we're talking about a driven damped harmonic oscillator, of course we have the force of damping, which is minus BV. We have the force of the spring, which is minus KX. But the driving force we assume is a periodic driving force with some amplitude, and the period of it is given at a particular frequency, which we call the driving frequency. And so what happens is our F equals ma becomes m d squared x dt squared is equal to minus kx. That's the restoring force, the damping force, and the driving force. So if we rearrange it so that we would be solving a differential equation, it would end up looking like this. And so it looks a lot like our damped harmonic oscillator, except instead of 0, now we have this term right here due to the driving force. And in terms of differential equations, this makes this a non-homogeneous differential equation because all the terms involving x are not equal to 0, but they're equal to this driving force. Now, the solution to this is rather complicated, but what we want to look at in particular is the expression for the amplitude of motion. The amplitude of the forced harmonic oscillator, you see, has all the terms that you would expect in, but also has a relationship to the driving force. And when we're talking about resonance, what we're talking about is the fact that we see that there's a particular value for the driving force where if this term is equal to 0, the amplitude will be the largest. And so we see that if we have values that deviate from the driving force, our amplitude won't be quite as big, but if we have the driving force at a particular, if we drive it at a particular frequency, we'll get the largest amplitude. And here we see the different values of the amplitudes. And so that's just sort of, again, for the damped harmonic oscillator and the driven harmonic oscillator, while there is a little bit of math, a lot of the understanding that I want you to have is a little bit more conceptual.